Morning, everyone. We are officially past the first week, which is always the most, I don't want to say chaotic, but it's got the most things change, add drop time, and all sorts of random odds and ends. So, now we're in it, good or bad. Things start mattering towards grades. So to that end, I'm glad to hear. I heard in the background people are doing the problem sets, which is great. Remember, the first quiz is due this Saturday at midnight. So, and remember, quiz, like, it's basically homework. You get 4 attempts on it. It's so many attempts. As long as you try it, you should get all the points, because the purpose of this isn't to actually, it's not for me to test your knowledge. It's for you to test your own knowledge, which sounds like the exact same thing. It's to give you feedback. It's basically for you to identify, am I understanding the concepts? And if not, then it flags concepts. Like, you can then look at those questions. You can go to me, you can go to TA, you can go to the help room. Speaking of which, I posted 2 announcements yesterday. At this time, every resource that I'm familiar with, so my office hours, the help room, and the SARC tutoring, I have posted the hours for all of those. So my office hours are in the simple syllabus. If you go to the announcements, I just made 2 announcements, one for SARC. So SARC tutoring is one of the things UCF offers. There's all the days and times. It's in the announcement. Check it out. SARC tutoring is led by an undergrad. And then the help room hours, also all led by undergrads. So this room is the one in Physical Sciences building. So just a quick reminder to y'all. Physical Sciences building is where my office is as well. It's where all the physics offices are. So reminder, this is us, Mathematical Sciences building. If you just go to the outer loop and go counterclockwise, the Physical Sciences building is the one. Let's go to satellite view because it's a little easier to show. The Physical Sciences building is the one in front of a parking lot. So if you just go a little bit counterclockwise past the Health Sciences, Physical Sciences building right there, the help room is literally the first door on your left. You walk in the front, literally the first thing on your left. It's right there. It's a room with whiteboards and lots of tables and chairs. Fits about maybe 20 people. It would be a little snug, but you could fit like 20 people in there. And then my office is the one in the back left. I've had a couple people here in my office hours, but feel free to come on by. I can fit up to 9 people. I have tea. I have snacks. So I have hot chocolate. All the good things. Come visit me or don't. I do love interacting with you all there and helping y'all out. But yeah, anywho, these resources are here. Use them for the problem sets. Use them for the concepts. Use them for the quizzes. All those things. The only thing you can't use them for is a test, because I'll be in class and all that jazz. Yeah.
On the syllabus, it still says the math sciences.
Oh, thanks. Yeah, let me just fix that.
What's the exact number or room number for your office?
Yeah, thank you. I apologize for that. I will fix that now. So my office is PSB 134. I'd forgotten that somehow it said a weird number here. PSB 134. Boom. All right, that should be updated now. So maybe that's why I didn't have many people. I don't know. Apologize if you went to PSB 13059. That's actually where I taught my other class. All right. And so last class, So last class, I left with this boat problem, and I promised you all I'd upload the worked out solutions, and I did. So if you go through, you'll find the slides. It's all worked out, so try it yourself. Do not start this problem with the worked out solutions in front of you. Just don't do it. Like, if you do that, what's effectively happening, you're more just memorizing the solution. You're more just seeing that, like, oh, that makes sense, that makes sense, that makes sense. Again, it's like saying I know how to drive a car because I watched someone do it. It's the same kind of idea. That's not how you learn. So use this if you get stumped. Use this if there's a certain part where you're like, I'm not getting the answer, I'm not sure. Look at this, figure out what went wrong, and then again, hide it. That's a good strategy for solving any problem in this class for learning. If you are just looking at the worked out solution the entire time, it's not effective. If someone is doing the problems for you, if you're working with someone and the way that they're helping you is they're just working them out in front of you and they're giving you every step, it's not helpful. As much as it may seem helpful, you will not learn as much unless your brain is having to struggle. As rough as that sounds, if your brain isn't hurting, if you're not feeling it, you're either not learning much or it's really, really easy for you as a subject. Those are kind of the two camps. Learning is hard. Learning is really, really learning is hard. If you're learning a lot of things, it's hard. It hurts your head. So, again, I compare it to lifting weights. If when you're lifting weights, if you don't feel any burn, you're not really gaining any muscle or burning any calories. Yeah.
So it's like the final answer to the problem, like it's almost like the dotted line. Is it like the dotted line?
It's this one. Yeah, it's along the dotted. It ends up basically being along the dotted line because the x and y basically cancel. The vector on the left, A, and the vector on the right, B, they kind of cancel each other out, left, right. So it ends up almost exactly pointed vertical. It ends up being 0.028 degrees, which is like 0 left. So yeah, it ends up being basically vertical due to symmetry and stuff like that. So that wasn't like, the dotted line wasn't to show you the direction it went. It just happened to be the direction it went. It's kind of a coincidental thing. I need to make a new version of this problem where it doesn't end up that way. All right. And then there's one last question I didn't get to, and I will not test you on this. This question is not one I can test you on. I mean, I guess I could make something like it, but this is a skill that I'll mention now, and hopefully I'll remember to continue mentioning. So it's approximately how many heartbeats are there in a lifetime? And this is a question that probably sounds like, how the heck am I supposed to know this? How am I supposed to, like, there's no numbers given in this problem. There's no, how the heck am I supposed to figure this out? I want you all to just try it. See if you can figure out how to solve this. I'm not looking for an exact, precise answer. I'm not looking for it's 5,376.537. No, like approximately. See if you all can get a sense of what you might do to figure this out. Spend some time. All right. Sorry. All right, for funsies, I'm going to try this out. I just sent it on Top Hat. I just want to see, this is a free response. Whenever I do a free response question like this, as long as you answer, you get full points for it. I'm not going to go through and check all the ones that are right. That's way too much work for me. So anytime I ask one of these these numeric answer questions, if you just answer, you get all the points. How are you? First week of classes, well, second week. The first week feels fake. Yeah. Alright, you got a threat. That sounds rough. That sounds rough. That sounds in the right ballpark. So what is this? I was just thinking sure. I was just thinking, okay, so I'm acquiring knowledge. Good. Sure. And then the average time went off the average life expectancy in the US. Good. 77. Good. So then I just 77 times that by 365 days. Good. Hours, 16 seconds, 2 minutes. And then I just times that by beats per minute to cancel out 3 minutes. Okay. Perfect. Perfect. So I'll say in a second. We call these back it off. But it's only we just do the process. This is a really useful skill to be able to approximate something that seems like a really ridiculous, like, how the heck would I figure this out? But if you just, there's roughly this many people in this many things in this many, you can actually get pretty close. It's kind of like if you say, like, here's something in your head. If you just get like a small area from in that, and you're like, this is approximately 20. Yeah. You can do that. Yeah. So, Oh, no. It's not coming up? Yeah, I mean, that makes sense. There's 0 responses. Oh, I know why. This just got sent to my lecture class. They're so confused. I forget that it defaults to the last class that I opened, and they all say 2053, so now they're all going to be like, what the heck? All right. Try to. Again, this top hat thing, I'm learning this with y'all. All right. Did it work? Yay. Anytime that happens, holler. Let me know. All right. No, you can't. Oh, no. Yeah, you have to go. That's the American answer. Yeah.
Oh my god. That's like literally minutes down here.
And then how many floors are there in the buildings? And then how many of those rooms do you think are occupied? Really? Yeah, and it's one of those, it's a super useful skill. It's a question that people do, like, how do you figure this out? But if you just phrase it in pieces, you can actually get pretty close. Really, really useful. Yeah, it comes up on. Alright, how'd you all do over here? Get a sense of an answer. Good. That's the one. It's like progress. Every human is different. Yeah. All right. Give y'all like 10 more seconds or something. I am encouraged by this. It seems like people are figuring this out, which is great. Even though I haven't really told you anything about how to do this. All right. And let's just see some responses. Remember, these are marked correct no matter what. Look at that. All right. So don't forget to do the scientific notation. Oh, let me rephrase that. Don't forget to put all the zeros. Yeah, like so I noticed that on one of them. Some people here I think just forgot to put all the zeros after it. But look, it's interesting that it alternates. Big number, medium number, big. I don't know why that's happening. That can't be on purpose, but that's very interesting. But look, all our answers are roughly within the same order of magnitude. So that's really interesting, even though I didn't tell you all anything. Even though I didn't give you all a single piece of information in this problem, it's interesting that you're all getting approximately, a lot of these answers are the same order of magnitude. Order of magnitude basically means how many zeros are there. Where's the decimal place located? So, anywho, great job. Gosh, what tolerance can I set for this thing? I don't know. I'm going to have to go back and figure this out. Correct answer. I'll go back and figure out how to grade this appropriately. You'll get points as long as you put something. That's all I care about. All right. So, what the heck is up with this problem again? We can see the different answers. We call this a back of the envelope calculation. Back of the envelope meaning that's how much space, think of an envelope, think how much space you have. It's not much. It's a very quick calculation that fits on an envelope. And you would be surprised at the things you can calculate approximately. I do not plan on asking you all questions like this on the test or things like that because they're a little kind of funky to grade and things like that because it's approximate. There's like a plus or minus here. But this is super useful skill. So another example of this is about how many average hairs does a human head have? Like, how would you figure that out? You do it the same way you do this. You break it into pieces. So the thing I saw people do here is they said, All right, on average, how many heartbeats per minute do people have? And some people said 70, some people said 80. I'm going to choose 80. Pick your poison. It doesn't really matter that much. These are like the fine details that don't matter. So there's 800 beats per minute on average. So in a lifetime, we just have to say what's the average lifetime? Let's say it's 75 years or something. 70, 75 years. Doesn't really matter. Let's say it's 75 years. So then with this in mind, we can kind of see, we just have to figure out how many minutes are in that many years. And that gives us an approximation of how many beats are in a lifetime. We average it all out. So there's 80 beats per minute. There is 60 minutes per hour. There are 24 hours in a day. There are 365 days in a year. And then we multiply that by 75 years. And you get something, this little squiggle here. This is the approximate symbol. You'll sometimes see this. It's not a straight line equal. It's a little squiggle. It's an approximate. It gives you a sense of what it should be. All right, and so 80 times 60 times 24 times 365 times 75. And we get 3, 1, 5, 3, 6, 1, 2, 3, 4, 5. 3 billion. Great. And you may be like, why do I need to know this? You don't. Like, this is not something, I don't know. Maybe this is useful for a doctor to know. I don't know why it would be. Maybe it would be. But we can apply this to lots of things. So, for example, one of the ones I gave, and it was great because I gave the example, and then someone said, oh, yeah, I am currently interning at a hospital, and they had us do this. Looking at a hospital and saying roughly how many patients does the hospital have in a day. It's like, how would you figure that out? You can, if you look at the building, you can look at the windows, and you can get a sense of how many classes there are, or how many rooms there are. If you're like, there's roughly this many windows and this much, and it goes around, you can guess, and probably get pretty close to how many rooms there are. Maybe, some might be hidden and things like that, but it's good enough. And then you look at the floors, and you say, the floors are roughly the same size, so just multiply the rooms by the floors. And then you take a guess at their occupancy. Maybe they're at 60% occupancy, 70%. You get a guess of that. You multiply all those numbers out, and you get a sense of how many patients go into that hospital every day. Or you could just watch the number of people walking into it. How many people go into a hospital? Watch it for a minute, or like 5 minutes. The longer you watch it, the more accurate it is. Then you make an estimate of if that's consistent or not. Multiply that out through 24 hours. You get a sense of how many people walk in and out of a hospital each day. These are useful things. This is just more like a life skill thing. A back of the envelope calculation, even though it's not precise, even though you don't have all the exact numbers, you will find that you will do these calculations from here, from time to time. And so it's just something, don't be afraid of doing this. Like, it's breaking a big problem into small pieces. That's what this is doing. And it gives you a sense of what's going to happen. So, useful skill. I wanted to mention at the beginning of the semester. I might mention it here and there if I remember. But just, you can do stuff like this. You can get an estimate of how many human hairs are on a head. Grab a pinch of hairs, estimate how many hairs that is, and then do that covers maybe like a 1/500th of my head kind of thing. Multiply it by 500 and get a rough estimate of how many hairs are on your head. Like, it sounds silly, but you can do a lot with this. All right, great. So just to do a quick recap of last week, don't forget units twofold. Units tell you in a problem what's given, and then when you write your answer, the unit actually makes your answer mean something. Make certain your steps in base units. I'll show you what those are as time goes on. Remember, vectors are arrows. Vectors are just arrows. They have magnitude and direction. They have a size, and they point a certain way. The direction is given by an angle. The magnitude is given by a number. And then this last one is going to come up again and again and again. When you are working with vectors, you have to break them into X and Y. You have to draw right triangles. If you're not good at drawing right triangles, a lot of problems in this class are going to be tricky. But it's a bread and butter skill that's going to also transfer to Physics 2. There's a lot of skills in Physics 1 that we're going to develop that when you go to Physics 2, you'll be able to use again. This is one of those. Another one is just how to solve problems. So, great. Any questions about vectors or units or anything before we move? Okay. Again, if you have questions at any point, so this is what the quiz is on this Saturday. Again, it sounds like a lot of people have done this, but I wanted to mention this problem because a lot of people were like, what the heck? But I think when a lot of people tried it, it went really well. So 1D kinematics. Man, what a bunch of jargon. It's 1D motion. Replace the word kinematics with motion. That's all it is. Kinematics is the study of motion. Moving things. Before I do that, though, Sophia has a joke. I didn't forget. Yeah, it's up to you if you want a mic.
No. So, Taco Bell is the only place you can still get gas for $1.49.
That's good. All right. I am a big fan of Taco Bell, though, so. Top 2 restaurants. Not restaurants. Top 2 fast food. Anywho. All right, 1D motion. So today's class is going to be how do you describe something's motion? And this might sound like an obvious thing, but we need specific jargon. And shock and awe, there's going to be vectors. You'll see why. But yeah, we're going to define common measurements, specifically position, velocity, acceleration. They're words you've heard before, but we're going to lock down the definitions to how we use them in physics. They're going to be what you expect, but with more precision. We're also going to talk about displacement. We're then going to find position, velocity, and acceleration using other things. And then we're going to also learn how to read graphs. So we'll be spending read graphs of position versus time, velocity versus time. It's graphs. So a picture says 1,000 words. A graph shows 1,000 data points. Like graphs are super useful for expressing data. That's why we're going to be using them in this class. And I'm just going to go ahead and show you all the slide, not purposefully to scare you. This set this week has the most equations I just kind of throw at you at one time. We're going to work through the equations and all that. But I'm going to show you to them now so you don't get as much shell shock when I show it to you for the first time. Let's see. Where's my nice slide with all of them? Okay. Here's the 5 equations we're going to be working with. You don't need to write them down now. Don't worry about that. I'm just showing them to you now. I'm mentioning it to you now that there's only 3 variables that show up in this. We're going to learn that x is position, v is velocity, and a is acceleration. And so when we eventually get to this, what I'm going to show you all is that the way that you use these equations is always find the variable you want. Say I want to find final velocity. So, let's say step 2, I'm solving for final velocity equals question mark. And say I give you x initial, x final, a, and t. Say I give you everything else. The way you're going to do these, and I'm only mentioning it now so it's less surprising when we come back to this later, you just find the equation that has what you need and has what you have. That's how you use these. These are actually very straightforward to use, even though it's a bunch of equations. They're really straightforward to use. And I'll go ahead and tell you all now that VF is the same as VT. These are the same exact thing. So we'll come back to this, but for now, I just want you to know it's really, really straightforward. It's way more straightforward than it looks. These can intimidate people, but you'll find that kinematics is actually one of the easier topics because it's so formulaic. It's very much write down your givens, write down your missing, literally just find the equation that has those things, and that's the one you use. Really straightforward. So, anywho, future things. Okay, yeah, kinematics, study of motion, woohoo. We need to be precise to define where stuff is located. And so we're going to talk about why that's important. Average versus instantaneous, all those good things. All right, so this is very sad. I didn't bring Demo Duck today. So Demo Duck is a big old rubber duck I have in my office that I forgot to bring. But that's okay because I thought about it this morning and I asked my daughter and she let me borrow Bulbasaur. So, what is Bulbasaur's position? That's the question for y'all. All right, decide as a group what the answer is. There's Bulbasaur. What is his position? Come up with an answer. I'll go around and see what y'all think. Oh, actually, you know what? Let's keep using Top Hat. Why not? I can ask these questions in here. Once you as a group come up with an answer, word answer. This way I can actually go through and see a bunch of people's responses without having to ask people. Yeah. Oh, and a reminder, Top Hat will start being graded Thursday, so don't stress about it too much today if it's not counted. But I am here to help you.
And then
Yeah, so there's a link on the yeah, it's its own separate thing. When you use the link I posted and then we'll have you and then on my end I did answer to
and he's
so right now
he's in front of the water bottle.
Alright, what y'all decide? Where are you at? Okay? Okay, because I was going to say 3 inches is water bottle. So this is my water bottle.
Oh, this is 3 inches. Oh, we could do the This is north. That's south. Yeah.
But you can see that like
so that's like
I do agree with yeah, nice. Alright. What you else say? Okay, more fish above the ground. Okay. Oh, okay. Okay. Stapler's all over. That's a good question. I like the way I do distances. I know I'm just so tall, so I think of how many of you lying down. Yeah, it's true. But that's why it's like, if you're depending on where you're at, you just like roughly. Yeah, no, it's every now and what is out there I get the option. Yeah, but anyway, that's a good idea. Alright, so let's see. Let's see what responses we have. I'll give you a few more moments. On the desk, origin, center of the room, standing upright, relative to still, positive. Whoa, look at this one. Forward facing east, approximately 3.5 feet off the ground, in front of the water bottle, 1.5 feet for the south edge of the table. All right, this is good. So this one is really detailed. Like, why do they put this much detail? I'm going to pick a random one, and I'm not trying to pick on anyone. I'm just going to pick a random one that's shorter, on top of the desk, standing upright. So, yes, but my stapler is on top of the desk. My calculator is on top of the desk. Everything on the desk is on the desk. So that does get us closer, but we're still not precise enough. So let me find one that's in between. Okay, on top of the desk, approximately 1 meter from the side ledge and approximately 0.3 meters from the front ledge. That's good. That narrows us down. We're on top of the desk. We're 1 meter from the side. It doesn't clarify which side, which sounds like a tiny detail, but there is 4 sides. And then 0.3 meters from the front. That's a bit more specific. So we know we're somewhere along this line, and that kind of gives us maybe 2 data points. So that's actually pretty good. Anyway. what I'm trying to make a point here of, and what's really good here, and again, I'm not looking for specific answers. I'll mark them all as correct. I'll go and figure out how to do that. If you have an answer, I'll give like 2 more seconds. Not that it matters because this isn't great this today. There's 2 things that people are doing that I really appreciate. People are giving numbers with units, so that gives me precision. But what was also important is a reference frame. If people are going to tell me 0.1 meters away, from what? You have to reference something to give position. So where this thing is located, there's an infinite number of correct answers to that problem, depending on what you define as your reference. Depending on what, and in our case, so you all have seen this before, a coordinate system has a reference, and that is the origin. The origin is our reference, where everything is measured with respect to. So in physics, what we're going to find is if I want to define this, I would need to pick a reference. Let's just say it's this water bottle. This water bottle would be my 0, 0. So I would say it's 10 centimeters in front of the water bottle. Its height is 0 because the water bottle is the same height as it. And then its left, right is also 0. We need 3 coordinates to define anything's position. And not only do we need 3 coordinates, we need to know what they're measured with respect to. If I told you something was 3 meters away, from what? 3 meters away from what? That's our reference, and in what direction. And so again, you can either give like angles and things like that, but this is one of the things with position. This is where I told you all, you've heard the word position, but for us to be precise, you need to have a reference frame. You need to know what you're measuring with respect to. And you generally need 3 coordinates, x, y, z, to be able to define exactly where it's located. So there you go. Now again, in this class, we're only going to do 2 dimensions to make your life a little bit easier. So position is measured with respect to a reference frame, and you get to decide where that, unless it's defined in the problem, you get to decide. Generally, it's defined. And it's located at some x position, and the I, remember, is that that's the x, and then the j is the y. So it's located at some x and some y, and the unit is meters. This is a vector. It has an amount, and it has a direction. Position is a vector because it points in a direction, and it has an amount. And we use R to kind of combine X, Y, and Z together. That's a pretty common notation that R is used for that. Lowercase r. All right, so now that we have position, that's kind of our, everything is, at the end of the day, a really interesting question gets to what can you actually measure in life, like hard measurements. Position is going to be like one of our foundational measurements. You can get a stick and decide the stick is my unit of measurement and then measure how many sticks away something is. We're going to find that almost everything else is going to be kind of based off of position. Velocity, acceleration, time, I guess, is the one exception. And even that's an interesting question. How the heck do you even measure time? You can think about that for a bit. But in general, the only things we can like hard measure are things that we can count. And then everything else is based off counting those things and doing some math. So the next one is displacement, which looks really fancy. And just to make this a little simpler, I'll get rid of this last bit. We'll just work in 2 dimensions. So I'm going to show you, this is, if you're familiar with Greek life, you'll recognize a symbol. This is delta. The triangle is the capital Greek letter delta. You don't need, I'm not going to test you about that. What is it? We run out of letters in the English language. You know, math, we want to express things in tiny little letters. There's only 26 letters in the English alphabet. We have way more variables than that. So we go to the Greek alphabet because we like the Greeks, I guess. This is delta. In physics, and you probably have seen this before, delta is the measure of change. So delta x is x final minus x initial. And you can see that down there. It's a change. Anytime you see this triangle in front of something, it's saying how much did it change? Final minus initial. And xf is final, x naught is initial. It's a little 0 for, beginning. We're going to see this a lot. So it's just measuring how much did my position change? How much did I move from the beginning to the end? That's what displacement is measuring. And displacement is very special in that it doesn't matter the path you take. We only care about the beginning and the end. When we're measuring displacement, we only care about the beginning and the end. This triangle, it just has 2 data points. Where did you start? Where did you end? Subtract those. I don't care if you took a squiggly line path there. I don't care if you hopscotch there. I don't care how you got there. You just went from one place to another. What's the distance between those 2 spots? So if I moved Bulbasaur from the left side of the desk to the right side of the desk, great. I moved him in a straight line. That's at some displacement. If I wiggled him around and moved him here, same exact displacement. If I tossed him in the air, same displacement. All that matters is where you start and where you end. And you subtract those 2. And you ignore everything that happened in between. And we'll talk about how that's useful and things like that. And you'll be like, that's so much lost information. A lot of times we don't care about that information. So we'll see that. Unit is meters. This is our base unit. So if ever you have a problem and it's centimeters, kilometers, decimeters, whatever other awkward units. I'm not going to give you awkward units. I'm not going to give you decimeters. But you need to convert it to meters. Just get used to that. Get used to converting things to the base unit of meters. All right. And I'm almost done jabbering and give you all a chance to do something. So displacement is probably a fancier word. You've probably heard the word before. Generally, I think it's often used for people who've been displaced from their homes, whatever. You've also heard the word distance. These mean 2 different things. Displacement is a vector, and you only care about the beginning and the end. Distance is a scalar, and it doesn't care about direction. What I want to add with distance, add. This is the part I want to recognize. Distance is the one that cares about the path you take. This is like counting how many steps you took. It's not steps you took, but like how far did you walk in a day? If you're wearing a smartwatch and it measures how far you've walked in a day, that's distance. Your displacement every single day. Actually, I'm going to ask this as a question because I think it's a fun question. So I'll wait a second. I'm going to ask you all the questions and think about it. What is your displacement almost every single day? So I'm going to give you all a second. I'll ask this. Every single person should roughly have the right answer unless you have a unique living situation. And, I'll even be kind. If you live in just one home, so some people, go home to home and that changes. If you live in just one home, what is your displacement each day? All right, great. Let's see what people have to say about this. I'll even put it as a word answer. If you're living in different homes, this answer varies.
Maybe.
I'm here, at the end of the day, ground, right back here. It's weird, but it's just getting that idea. What the word displacement means. So it is useful. As weird as it, like, what's the point of that? It is useful. Yeah. So for now, y'all trust me that this is useful, even though it might not seem like a useful quantity. It's like what? It is useful. All right, I'll give you all like 20 more seconds. Again, I guess, am looking for a specific answer here, but as long as you answer these 3 response ones, you're going to get the points. All right, and 3, 2, 1. All right, let's see what these responses look like. Again, they don't have names, so I don't feel bad about showing it. Ooh, interesting. It does like tally up the people that said it. 0. Ooh. Okay, so technically there is a right answer, and only 6. Don't forget your units, y'all. 0 what? 0 what? I was like, it sounds silly. Again, you get the right answer no matter what, but I appreciate that people thought about that. The answer here, so in the morning, you start where you sleep. Bed, couch, whatever you sleep on. Floor. At the end of the day, I assume most people sleep in the same place. I don't know. Some people might vary to keep things interesting. I sleep in the same place, but everyone's got different lifestyles. So if you start at the same place and you end at the same place, the displacement is 0 meters. That was the point of this problem. You have hopefully left your bed that day and moved around. Your distance is not 0, but your displacement is. And we're going to use displacement for various things. It is useful. This problem was an extreme just to get the idea across of the difference between them. All right. Great. To that end, let's try a couple more. This one actually has a right answer. You can actually check the answer in this. So if a car goes once around a roundabout, if you're not familiar with the roundabout, those are the circle things. They're more efficient than traffic lights, all that good stuff. With a radius of 20 meters, what is the distance traveled? Is the answer 20 meters, 125.67 meters, 0 meters, or 40 meters? What is the distance? The word asked matters.
Is the radius?
I told my daughter I'd send her pictures of both for work. So. All right, give y'all like 5 more seconds. There's only one right answer here, y'all. In 3, 2, 1. All right. So this question gets down to its distance. What's the definition of distance? How far you travel. It's literally how, like, again, if you're driving a car, it's what your odometer is reading. That's when they count your miles. If it's your smartwatch or whatever, it's how many miles you traveled or kilometers you traveled in a day. So you draw a picture. What path did I take? A full circle. I went around the entire circle. And then you have to remember, how do you measure that distance? Circumference. And when you do that math, there's only one answer here that actually works, even without plugging it into a calculator. 2 times 20 is going to be 40. 40 times anything is going to be bigger than that. So it's 125.67. But just to show you all, 2 times pi times 20. You plug that in, you're going to get that answer. Great. If you found 40, that's the diameter. And that would be if you just went straight across the circle. If you didn't actually go through the roundabout and you just said, forget it, and you just went straight through it. But this time we did a full roundabout as well, so that wouldn't work either. All right, great. Next question. You can probably guess what it is. Same exact question. What is the displacement? 20 meters, 125.67 meters, 0 meters, 40 meters. Alright, I won't give you all too much time for this one. I'll give you like 20 more seconds. Go with your gut. Since we've asked a similar question to this already. All right, 5 more seconds. 3, 2, 1. Oh, and this is where I'll warn you all. If you are online when doing these top hat questions, I have my stream going on. Even though I've set it to ultra low delay, every stream has some delay. Maybe that's 10, 20 seconds, 30 seconds. Normally it doesn't matter. It probably does matter if I say there's 5 seconds left and you're online, because 5 seconds, when I said that, that was 25 seconds ago. So be warned, if you are doing this online, just kind of like I will send this question to the devices as one of the benefits. It sends a screenshot. That's great, so you can still see it in advance, like all that. But do not use my timing as like an indication. If I say 5 seconds left, that's gone. That's passed. If you're watching the stream, I mentioned that in the off chance you're watching the stream. I want to note that. If you're in class, obviously our time is pretty consistent. We're pretty close to each other. There's no delay, roughly. All right, great. So, what's the answer? I forgot to mark as correct, but I'll go back and do that. It's 0. Same thing as before. You start and stop at the same spot. Displacement does not care. Sure, I went in a circle. Who cares? All that matters is I started and ended at the exact same spot. Started here, ended here. What's the distance between those 2 dots? 0. That is displacement. All right. So, another question for you all, just to make things interesting. Again, I'm not going to ask this one. After you sit in your chair for 5 seconds, why is a possible displacement not 0? This is just a fun question to think about. So go ahead and respond to this one. Same thing. I want to see what your all's thoughts are. I like this, being able to actually get free response. It's fun to see people's thoughts on this. What's your thoughts? Let's say you don't move at all. You have no ability to move. Irrelevant. Semi-relevant to your research. choosing a good reference frame, being specific about it. If your reference frame is this room, reference frame is the sun, we're moving. Reference frame is the greater black background, we're moving. It's just an interesting thing. Alright, what'd y'all say? Ooh, yeah, good, good. Yeah. So in each case, what do you change? So I guess there was a phrase I used before. Well, you're changing your reference. What's your origin? Where are you? Remember when we said where is this guy located? Where are you measuring with respect to? If you measure yourself with respect to the chair, you're not moving. But if you're measuring yourself with respect to the sun, you're stuck on the earth and you're moving with the earth. But even the earth itself is rotating. So if you compare yourself to the star, whatever. Yeah. But it's just an interesting. Alright. Give y'all like 5, 7 more seconds. And then while I have the big list of things, I'll let people share out theirs. Because this is a fun, like, aha thing when you kind of realize why this might not be the case. All right. 3, 2, 1. All right. Great. Who's got some ideas? Yeah.
Because when you're sitting in a chair, you move it left, move it right, move it forward, move it backward, especially if it has wheels.
That is true. I did not clarify that the chair wasn't moving. Didn't even think that's a clever solution. Didn't even think about that. You can actually move the chair. That's not a. There's no thing restricting that. That's good. That's a good idea. Didn't even think of that. Yeah. The earth is moving, and so when you all are measuring, when you're saying you're not moving right now, what are you comparing yourself to? The earth and everything kind of in it. You're comparing yourself to the chair, to the room, to the walls, everything that's kind of attached to the earth. That's your origin. That we call that a reference frame. That's what you're referencing. What if you compare yourself to the sun? You're on the earth. If the earth moves, you move. So it's an interesting what you're comparing. Again, the reference frame matters. Answers. What is your displacement? The answer is actually there's infinite answers for what your displacement is right now, depending on what you reference. The answer, there's only a finite answer. There's one right answer if I say with respect to your chair, with respect to the sun, so on and so forth. So interesting things to think about. It's kind of like when you're sitting in a car, you don't realize you're moving unless you look out the window. Same if you're sitting on a train, you don't realize what you're moving unless you look out the window. When you change your reference frame, your answer changes. And so that's going to be a really, really important trend in this. Yeah, so let's see. You move, Earth moves. You can move your chair. Technically, you could slightly wiggle a bit and things like that. Yeah, good. All good things. So, great. All right, so let's jump to a question with actual math. So this is always how kind of we're going to do things. We'll talk about the concepts. We'll do some conceptual questions. And then we'll kind of end that chunk with some like actual number solving. Funny enough, the conceptual problems people can miss just as much as the math problems. So when you're all studying, make sure you look back at these top hat questions. Make sure you understand them. So position of a particle along the x-axis is given in meters by the following equation. X of t equals 4 minus 2t. At what time does the particle cross the origin? And what is the displacement of the particle between 3 and 6 seconds? Something I want to point out with this equation, equations are just a machine. It took me a little bit to really understand this and appreciate this, but the second you do, the easier things are. This x of t just says when I plug in t, I get x. That's all that expresses. Anytime you all see that like y parentheses x or anything like that, it just says when I plug in time, I get x. That's all that represents. It's like equations are just machines. You put in something, you get out something. I put in time, I get out x. I get where I'm located. So try this out. I'll put the answer in a second. I'll wait a little bit. But I want you all to try it out as a group. Remember, there's only one right answer. If you're like, man, I really want to check my work, the answer's in the problem set already, so that's where I'm going to get the answer from. So if you want to look ahead and check yourself, it's there, but I'll put the answer in just a little bit as well. Work together.
To find the A, I think you have to, you just plug it into the origin zero. Is that what we're doing? Yes, is the origin at zero? So. No, sorry. So, what made you put in zero? When I make X zero to origin, do I have to divide it? Okay, so if we're trying to find the origin zero, I take X and make it zero, phi to the that
No. That's all right.
Oh, shoot.
it's one more thing. I didn't break it apart. Okay.
How do like I feel like I never know how to ask questions.
Sure. Yeah. So one of the things I often do when I go to so if they give me the thing, first I say, okay, what do you have? Like, what have you done? That just gets a sense of where they're at. Next, I go through the problem-solving process. All right, what's given? What are we solving for here? So in this case, what time does it cross the origin? Okay. What are we solving for? And then they think about it, and then I might follow up and say, what does it mean when I say cross the origin? What does that mean variable-wise? Because that's a lot of what the problem step is, write it in variables. So in this case, it means when does x equal 0? But I try to get them to that point. So that's what it ends up being. But then you ask them, why did you set that at 0? Yeah. So
But
that is how you do it. Yeah. Because the origin is when x equals 0. And so we're solving for when x equals 0. Yeah, so the question is so those are the kind of questions. Maybe I'll have to ask them, why did you do that? Yeah, whenever you're working, we'll ask questions. And then when they kind of explain it to you, like, those asking questions for most students. Yeah. Yep. What is specific so how do we find the she's got it. So she's got the sensitive, so check with her. She just said. Yes. Sure. So let's yes. What is it? There's two parts. All right, so it's looking good, y'all. And again, so how do we solve this problem? Problem solving process. And there's a couple things you all can do here. So remember I mentioned you can draw a picture. So in this case, you could draw a graph if you really wanted to. There's no harm to doing so, and I saw people do it. So if you're good at drawing graphs, there's the, t-axis. So it's a little weird because here, x, you're so used to x being on the x-axis, right? In this case, time is what's changing and position is what's being affected. It's x as a function of t. So x actually goes on the y-axis and t goes on the bottom. So that's just a good kind of mention here when we do graphing. So in that case, our intercept is 4, and then it's got a slope of 2t. Yay. Okay. At what time does the particle cross the origin? So actually, let's just write down our givens now. What's given? We got a function. So this function tells us where I'm located at some time. That is the given. That's all we got. Step 2, and this is where maybe things might fall apart. At what time does the particle cross the origin? So we're solving for time when, what is the origin? When x equals 0. The origin is when x equals 0. And now we can put all that together. So what are we going to do? In this case, the equation is what I have. 0 equals 4 minus 2t. When is x 0? That's what the question is asking. So this is a little bit of a lot of the challenge in setting up a physics problem is taking the words, understanding what they mean, and doing it. And so that takes practice, but you practice enough, you'll get it. And yeah, you rearrange this, you get 4 equals 2t, solve for t equals 2 seconds. That's part A done. So I'm going to go through kind of both, and then the next part B is going to have its own setup. So that's the idea here. Once you know what you're doing, it's like, okay, that makes sense. You just have to really realize that x equals 0 is the origin in this case, because we don't have multiple dimensions. All right, for part B. Part B, I'm just going to steal all this. It says, what is the displacement? And so much of physics problems is, do you understand what it's asking for? That is so much of when you're solving physics problems. Do you understand what it's asking for? Do you understand what the things mean? So in this case, what is the displacement? So I'm just copying things over, and then I'll delete the things that are not relevant and fix them. Okay, so we got our same given, yay. But now we're solving for something different. Erase all the old things. We do have a new given. And I'm actually going to write this in our fancy term. Our t initial is 3 seconds, and our t final is 6 seconds. Question you might ask is, it's going to sound like a silly question when I say it out loud. How do you decide which one's initial and final? Initial is a smaller time, final is a later time. That's how you make that decision. Sounds obvious once you say it, but sometimes just you can get caught up on that. All right, displacement is r. That's technically like the variable for it. R equals question mark. And then this is where you have to ask yourself, what the heck? How do I find r? How do I find? Oh, and sorry, displacement is delta r. Regular r is position. Regular r is where you're located. Delta r is position. How do you find displacement? And this is where you have to remember that it's the change in x. If there's multiple dimensions, we'd have those. You know what? I'm just going to put all of them. But there's no y dimension, so we don't need to worry about it. Okay, great. What does this mean? Remember, y'all, it's x final minus x initial. Displacement is the final minus the initial. And so that was a common question I got. It's a very valid question. So all you have to do is find those things. So how do we find x final? Well, x final is going to be when t equals 6 seconds. So you just plug that in. 4 minus 2 times 6. That's going to be negative 8. When's x initial? It's when t equals 3 seconds. And that's going to equal negative 2. And so you just do, so my delta r is xf minus x naught, negative 8 minus negative 2 equals negative 6 meters. The negative means something. And I put that in words for the answer. Negative 6 meters means I move to the left 6. That's what it means. So actually I should fix the wording here. I put negative 6 meters to the left. That's not actually the right I moved 6 meters to the left. Displacement is not about where you're located, it's how much you moved. So in this case, the displacement means I moved 6 meters to the left between those two times. Doesn't matter the path you took, just matters that I started somewhere. 3 seconds later, I'm 6 meters to the left of that. But negative 6 meters is perfectly valid as an answer. I only put the words here to help you understand what the numbers and letters mean. And yeah, never forget your units. So there you go. That's position, that's displacement, where you're located, how far you've gone, all that good stuff. All right, I will introduce one more thing. Well, this is a good stopping point. We'll take a break. So we'll take a break till like 9:15 on that clock. On the real clock. It's 9:08 on my real clock. I can't fix these clocks times. I have to contact people to do it for me. It's stupid.
I think the function notation tripped a couple people up.
100%. Yeah.
Some people are like, oh, so x times t equals.
Yeah. And that's going to recognize an x of t is x final. Yeah, it takes time. Hello. Sure. Okay, so equation, good. And then really the challenge here is what are we solving for? When I say what time are we at the origin? What does it mean for us to be at the origin? Not starting, that x equals 0. Yep. This is just x.
Okay.
This x of t is just where am I located at some time.
It means x depends on t.
Yep. So we just replace this with 0. This is x at some time. Well, we know x at some time. 0. And then you just solve for t. And that tells you when I'm at x equals 0.
And how did we get 0? Because we started from the origin from the question?
Yep.
Yeah, we're looking for when we're at the origin, and
That
the
is
origin
specific.
is where
Yep.
you've chosen.
And so it's key to what the question's asking. It's saying, what's the time? When? What's the time when I'm at the origin?
So if you would have given us like a number for
Yeah, exactly. It could have been like, I could have reworded this as, what's the time when x equals 0? It's the exact same question. Or I could have said, what's the time when x equals 5? That's a different question, but it's the same process. Yeah. Hey.
My campus is not working, so I can't access like a
Okay.
schedule yet. I let the school know, so
Okay.
they're working on it.
Sure.
I've been having a little bit of a health issue.
Okay.
And I have an appointment on the 11th of February.
Okay.
I don't know if you have anything going on.
Tuesday or Thursday?
I think it's a Tuesday.
You won't be, the only thing that gets affected, so just give me a heads up and I can give you the top hat points for that day or whatever. Send me an email, things like that. Yeah, happy to work with you. Yeah. Sure.
Unless stated otherwise, will the origin always equal 0?
The origin is always when every x is 0, y is 0, z is 0. If ever there was more dimensions, all the things.
But you could say to the origin x equals 2. You can say that, or is it always?
It's always 0. Yeah, the origin is always 0, 0, 0, 0, 0.
So at this point in this example, you always try to find
When x equals 0. Finding the time. When. Yeah. So we're finding where it intersects from here. When does x equals 0? Yeah. So it's not, because clearly this never hits that, because you're thinking that in that case, if we think about that, we're thinking about it as an XY plane, but it's not an XY plane. Yeah. So it's asking when is x equals 0. Yep. It's a good question. And I might make it.
It's like we always like have a better answer. It's like we have It's like I never actually did research on like a guy who actually but what's happening is so my x value is so this graph has actually so this is fun, right? So as time goes on, how do I know that? Because later my x value is so what's breaking right here is not an xy let's make it but all of them is like and then for the next year I just when am I looking
It's probably fine. So basically, this that I've done with
All right. So this graph, I think the thing that I want to talk about it. Let me walk out this graph. Let me actually walk what this graph is doing. One of the things that you have to get away from in your mind, you all are, is that you've always seen graphs that are x versus y, x versus y, x versus y, x, like always. In this graph, though, the left and right is time. What that means is that when you're moving to the right, you're moving forwards in time. So when I move this way on the graph, I'm moving, that's fast forward. When I go to the left on the graph, I'm playing the video in reverse. So this graph moving to the right is forwards in time, moving to the left is backwards in time. It's not location. Moving to the right on this graph is not, I'm moving to the right. Moving to the left on this graph is not moving to the left. The x-axis is time. And what is time but which way you're moving in time? Like, what is time? What a weird question. To the right is forwards in time. To the left is backwards in time. And so then, what the heck do the up and downs mean? So this is reverse, forwards in time. I'll put that there. What does up and down mean? So up and down, what's our variable there? It's x. Up means I'm in the positive direction. That means I'm to the right. Left, if I'm above this axis, I'm to the right of the origin. If I'm to the left, or if I'm below this axis, so anything above this is to the right, anything below this is to the left, because it's x. Positive is to the right, negative is left. It is not up, down. You have to, so the key here, and one of the new skills is realizing, depends on what variables are on this graph. So, to that end, let me walk this graph out. I have to pick an origin. Bulbasaur is my origin. Great. So when x equals 0, this is x equals 0, okay? Bulbasaur is x equals 0. So at time equals 0, t equals 0, where am I located? At time equals 0, we're going to say that's when things start. Where am I located? What's my x value on this graph at time equals 0? Plug it in. Plug t equals 0 and tell me where what I get. 4. If y'all plug in t equals 0, 4 minus 0 is 4. So at time equals 0, is it positive 4 or negative 4? Positive 4. That means I am 4 meters to the right of Bulbasaur. So at time equals 0, I'm located at 4 meters. Now a little bit of time passes. What happens to my x value? Does it become bigger or smaller? Smaller. Do y'all see how the x value as time goes on gets smaller? So I'm going to approach, as time goes on, I approach Bulbasaur. I'm getting smaller and smaller and smaller. And at time equals 2 seconds, I'm at 0. And as time goes on, I keep moving in this direction. So that's what this graph represents. As time goes on, my x value is getting more and more negative. Okay? Now, good news is, we're going to get more and more practice with this because the slope of this line means our next variable. The angle of this line, how much my position changes with time, is going to be our next one. So if that doesn't make sense, then we're going to get more practice with it. So to that end, again, I don't have demo duck. What is Bulbasaur's velocity right now? You've probably heard the word velocity. If not, pretend like it's speed for now in your brain. All right, same thing. I'm going to see what y'all's answers are. What is Bulbasaur's velocity right now? All right, give y'all like 20 more seconds.
Next time.
All right, in 5, 4, really slow countdown. No, you're fine. No, I want, if that happens, like if you are still answering, holler out, and I'll start counting really slow. 3, 2, 1. All right, let's look at the answers. 0 meters, 0 meters per second, 20,007. Ooh, I like that one. Meters per second, 0 meters per second relative to Earth. So interesting looking at these. What I appreciate, as long as you had a number and a unit, your answer is right. As long as you had a number and a unit that represents speed/velocity, it's correct. And the question is, how the heck are all the, how is this 20,784.8 meters per second? How is that correct when 0 meters per second is also correct? What are you measuring with respect to? Remember, the reference frame matters. Relative to this desk, how fast is he moving? 0. Relative to the sun, he's attached to the Earth. The Earth is moving, which means he's moving. So with respect to the sun, it's actually an incredibly fast velocity. And in fact, the whole solar system is moving. So then if you looked at the velocity of him relative to the galactic core, whatever the right phrase for that is, that's even faster. Depending, I guess, on which way the solar system is rotating. And then if you look at that with respect to, there's so many reference frames you can pick. And when you're doing space science, you care about those things. Depending on what you're doing, you may or may not care about different reference frames. But yeah, velocity. It's how fast you're going. It is a vector. The direction matters. So it is a vector. It's got a little arrow on it. The direction of this matters. I need to put that somewhere. It is a vector. Direction matters. Remember, left is different than right. You never get to Tampa if you're going north. Not happening. Yeah. And then the variables here, average velocity, you take your displacement, to remind you all, this little delta r, this is just displacement. So if you can figure out how far you've traveled, and you divide that by your time, then you found out your average velocity. Average velocity. And it's the slope of a position versus time graph. Rise of a run. And I left something here from calculus. If you're wondering what the heck this D is, that's from calculus. That's a derivative. Well, infinitesimally small size. You don't need to worry about derivatives. And technically, I'm also going to remove this because I realize now it's not at some specific time. So a little bit more accurate. Doesn't really change. Average is just displacement over time. I put any of these graphs. All right, and I'm actually going to steal this last question. I didn't put this here before, but I'm going to now. So you know what? I'm just going to steal this whole slide with all the writing on it and everything. Delete some things. The position of a particle moving along the x-axis is given in meters by this. What is the velocity? And the key here is, I'm going to point out this picture. I'm not going to actually put it in writing. What is velocity? It's rise over run. Your change in x over your change in time. Rise over run. So with that in mind, given this, I even drew the graph here. What is the velocity? And I'll give you all some time to try it out. This one I won't have a response to, but I'll give you all a few moments to think about it. All right. So the key here was in the picture. Velocity is the slope. Rise over run, that's slope. How much does my position change with time? Literally, so think of the units for this. The units for velocity are meters per second. How many meters do I move every second? That is the slope of this line. So if y'all look at this line, I mean, you can see it from the graph, but you can also see it from the equation. What is the slope of the line? The velocity is -2. If you're like, how the heck did he do that? Remember y equals mx plus b? Oh, that's true. -2 what? What's the units? Yeah, good. Thank you. Please do catch me on that. the slope of this line is -2. And you're like, but how, what if I don't see that? Pick, in this case, this is a slope. So we talked about this during our lab last time. So actually you all saw this a little bit in our lab last time. The slope of this is the velocity. You can pick any two x values. You can pick any two times. You can find x. So you could find x of 2 seconds and x of 0 seconds. So x of 2 seconds is going to be 0 meters. X of 0 seconds is 4 meters. So if you want to do the math, and I didn't give myself nearly enough space for this, we could do the following. Remember, velocity is delta x over delta t. So I could find the velocity at x equals 2 seconds minus the velocity of x equals 0 seconds and over the time. At 2 seconds, the velocity, you just plug in the numbers. It's 0 minus, what's the velocity at 0? 4. Oh, look, you get the same exact answer. How do you find the slope of a straight line? Just pick any two spots. Like, it's just funny. You all know how to find the slope of a line. Like, that's something you've done a lot. That's all we're doing here. Velocity is the slope of this line. It's a constant velocity at every single spot because it's a straight line. So remember back to my example where I actually walked this out? This means I'm moving to the left at 2 meters per second. That's what this means. So it's maybe a little bit easier to kind of understand this. As time goes on, my x position is changing by -2. Every second, I'm -2 to the left. After 1 second, how far have I moved? 2 to the left. After another second, how far have I moved? Another 2 to the left. After another second, how far have I moved? 2 to the left. If the velocity is constant, that means you're always going in that direction, and every second, that's how far you're traveling. Negative means to the left. Positive means to the right, if you're in the x direction. If you're in the y direction, positive means up, negative means down. Okay? All right. And don't worry, we're going to have lots of practice with that. Okay, so try it out with some numbers. If an object starts at x equals 2 meters and ends at x equals 10 meters, if it takes 4 seconds, what is the velocity? I'm even going to be so kind and graph this for you. You know, yeah, try graphing it too. See if you can do it. If this is an easy problem for you, draw the graph of it. Assuming a constant velocity. We have to assume that. And there's only one right answer here. No, but that's good. That's good. But it all works. Yes. No, that's good. But the fact that good response. You have the right idea. It's one of those. That'll happen. You're gonna make lots of silly mistakes. I'm gonna make lots of silly mistakes. The important thing is when you say it. See that when you yeah, good. Yeah, what do we got? What's good in this one? Good. We got our. Which one's our start? Yeah, which one's our start? Good. What else?
So at 0 seconds. What's our x position? And then at x equals 4 seconds. Connect the dots. As time goes on, every second.
All right, give you all like 10 more seconds on this, then I'll walk through it. All right, a few more seconds. Put down your guesses. Don't worry, I'll show you all how to do it. If you miss these, it's not the biggest. It doesn't really change much in life. All right, so I'll even leave the responses up. I'll even give you a chance, but I'm gonna go through the steps. What's given? And so when you're writing the givens, we need to write them as variables. That's what's gonna make your life easier. We need to translate all these words into math, into variables. So, y'all tell me what's given. What variables? X initial. So we represent X initial as X naught, X final, XF. All right, great. Yep, which one's X initial? 2. How do we know that? Again, this is translating. Math is a language. We're translating English to math. Starts at X equals 2 meters. Meters. So I could have said an object starts at 2 meters. Now I kind of have to tell you, I guess that's an X coordinate or Y. So that's why I put the X here. But the meters tells me its location. Starts tells me its beginning. Process of elimination, 10 meters is the final. Great. What else is given? 4 seconds. And this one's going to be a little bit more subtle. What variable does that go with? Delta T. This is not T final. This is not T initial. This is the amount of time that passes. It's delta T. This is the amount of time that passes. So that's final. It's already done. Final minus initial is done. And if you really want, you can assume this is T final and make T initial 0, but that's technically not 100% guaranteed. All right, great. We're solving for average velocity. That's fairly straightforward. It just straight up says what's average velocity. So when you're writing your givens and missings, you're going to do it like this, in variable form. Because when we do step 3, we just find the equation that has average velocity. Y'all tell me what's that? V average equals what? What's the equation for it? Delta X over delta T. If we're in one dimension, this is true. If we're in multiple dimensions, I'm just going to warn you, it's that R. We'll see that in a couple weeks. But since we're in one dimension, and then you can write this as XF minus X naught. And ta-da, now we just plug and chug. Kinematics is very much formulaic. Write down your givens, find the equation. V average equals 10 minus 2 divided by 4 equals 8 divided by 4 equals 2. And it's always good. What the heck does this mean? It means every second I'm moving to the right 2 meters. After 1 second, I'm 2 meters farther to the right. After another second, I'm 2 meters farther to the right. That's what velocity means. If you're traveling 30 miles per hour, what does that mean? Every hour you're traveling 30 miles. In our case, we also have positives and negatives. Positive is to the right, negative is to the left. Last challenge for you all is to draw this as a graph. If you didn't do so, this is a good it's a good practice. Now, technically it's not, we don't actually know what happens at t equals, we're just going to say it starts at t equals 0. It's not clarified here, but we're just going to assume that just so we can actually do this exercise. So at t equals 0, what's my position? Y'all tell me. At t equals 0, what's my position? Where do I start at? 2 meters. So I put a dot 2 meters up. And I definitely didn't give myself enough space for this. All right. 4 seconds later, at t equals 4 seconds, where am I located? 10 meters. So after 1, 2, 3, 4 seconds, I'm somewhere way up here. And in this case, we're just going to assume a constant velocity. And that's the graph. As time goes on, I get 2 meters farther from the origin. Every second, I'm 2 meters farther. Another 2 meters, another 2 meters. If I go backwards in time, I end up back at the origin. So on and so forth. So, there you go. The beginning of this class is the hardest part of the class because I'm having to teach a lot of things at once. We talked about vectors. That's a whole thing. We're talking about how to even do this, translating a word problem into variables. That's a whole thing. The skills you're developing in the beginning of the semester, it's a lot all at once. So it's okay for this first few weeks. They're going to be, in my opinion, the hardest part of the class. And I say hardest, not to mean that they're hard per se. That's going to vary how much you view this as difficult or not. But it does get easier as you develop these skills, as you get better at this. We're going to use the same strategies throughout the entire semester. So give you some peace of mind. All right. These are some key phrases you all need to know. Again, towards the end of translating words to math. At rest, stationary, still, not moving, sitting still. Anything that says that an object's not moving, you have to translate in your head. That's a given. That's v equals 0. Your velocity is 0. How fast is Bulbasaur moving? 0. In a problem, they're not going to always give you every number. Some of the numbers are going to be hidden in words like this, i.e., can you visualize the problem and understand, oh, it's not moving, v is 0. Or at the end, it's not moving, v is 0. This is a skill, and it's one of the, again, it's can you translate words to variables? That's the skill. It's going to come up. It's going to happen a bunch in this class. So I mention it explicitly here because you know this. You know if something's not moving, its speed is 0. You know when your car is parked, the speedometer is 0. Just making certain you translate that knowledge to these problems because you're going to need that. All right. Already mentioned this, and I need to change this from a d to a delta. Remember, just the slope of a line is the velocity. Like, already mentioned that a few times. For those that have taken calculus, the integral is how you go backwards. Don't worry about that. You don't need to know calculus. But if you have the derivative of a position versus time gives you velocity, the integral is a backwards derivative. That's only for those that have taken calculus. If you haven't, pretend like I didn't say anything. You don't need to know that. Okay. Just like we had distance versus displacement, we have velocity versus speed. Velocity is a vector. The direction matters. How fast you're going and in which direction. Speed is just how fast you're going. Just how fast. Doesn't tell you anything about which way you're going. Cop pulls you over, you say how fast are you going. You tell him 70 miles per hour, that's speed. If you told him I'm going 70 miles per hour east, 30 degrees of north, you've given him velocity and he doesn't care. That's the difference here. In physics, we care about the direction. Direction matters. It gives us more precision. It helps us predict what's going to happen. So if I ask for velocity, I also generally want the direction. I generally make that explicit. Give me the magnitude and direction. If I ask for speed, just give me how fast you're going. Just the number. No positives, no negatives for speed. Speed is the absolute value of velocity is another way of thinking about this. We're not really going to use speed too much, to be honest. Velocity is usually what we're going to use, but like even that variable s, like that never shows up in equations. We never use s in equations. But v is the go-to. All right. Okay. A cyclist rides 8 kilometers east for 20 minutes. And then he turns and heads west for 8 minutes. And travels 3.2 kilometers. Heads west for 8 minutes and travels, that's missing a word, 3.2 kilometers. Finally, he rides east for 16 kilometers, which takes 40 minutes. What is the final displacement of the cyclist, and what is his average velocity? And this is going to look complicated. But first thing I need to teach you all, this is going to sound stupid, but which way east and west is, and the chance that you do not need to know this on tests. On tests, I don't generally use north, south, east, west. I just use up, down, left, right. But just for your general knowledge, never eat soggy waffles. Never eat soggy waffles. Great acronym to remember to know this. It is useful. But again, on a test, you don't need to have this memorized. I'm just going to use up, down, left, right on tests. The way I want you to start this picture is, the way I want you to start this problem is draw a picture. So I'll give you all like 30 seconds, a minute, a couple minutes. Draw arrows. They go east 8 kilometers. Draw an arrow for that. Then they go west 3.2 kilometers. Draw an arrow for that. Then they ride east for 16 kilometers. Draw an arrow for that. You should have 3 arrows all connected kind of together, and they all point left or right. So try that out, and I'll give you all the answer in a second. That'll be our first thing, because if your picture is bad, the whole problem's bad. The key here is wherever the first arrow ends, that's where you're going to start drawing the next arrow. Then wherever that ends, then you're going to draw the next arrow there. And make sure your arrows are scaled appropriately. 8 is bigger than 3.2. 16 is bigger than both of those.
I guess time. Because I'm assuming time is going to be the one in distance.
So which way is this start? What's our beginning direction? Perfect. Let's draw an arrow to the right. So big is that arrow? How far do we go?
The directions are not. He's going east and west. He's not
Perfect.
going in an angle.
All right, great. Now what?
So you don't have to draw them that way, but it's just east and west. You can like stack them as long as the direction.
Are we gonna let you solve this problem then?
So
Nice.
displacements start that way. So.
Okay. So, yep, we just draw these arrows. So which way do I start moving? Left or right? Right. I move east 8 kilometers. So there's an arrow. That's 8 kilometers. And I saw someone do this and I thought it was a great idea. Kilometers. Immediately, that should be a little bit of flag in your head. That's not the base unit. You convert it. Do unit conversions sooner than later. It's okay if you put 8 kilometers on this arrow here. It's not wrong. But the sooner you do unit conversions, the less likely you are to make a mistake later on. The less likely you are to forget to do it later. So 8,000 or 8E3, you could put 8 kilometers, that's fine. But you need to convert it at some point. Anytime we say something that's not in base units, you're going to have to convert it at some point. Do it sooner than later so you don't forget. All right, now which way do I go? Left. How much? 3.2. That's a slightly smaller number. A little bit less than half. So we go 3.2 E3 to the left. All right. And then last, which way am I going? To the right, how much? So we draw a big arrow that's roughly exactly twice as big as the first one. 16 E3. All right. Now my challenge to you all. Draw the arrow for displacement. Draw an arrow that goes from the beginning to the end, because that's what we're solving for. So it's good to be able to draw that visually. Draw an arrow from the very beginning of where I started to where I ended. Do not make your arrow go up or down. I couldn't stack these arrows on top. If I stacked them on top of each other, it'd be hard to read. Remember, we're only traveling left and right. So please, your arrow should not go up or down. It should just go left or right, because that's the only way we've traveled. Give you a few moments for that. So we started right here. We ended right here. So this is my displacement. That is what we're solving for in this problem. How big is that arrow? Start to end. Now get it. Yeah, I just drew an arrow for how far I went. This is my delta x. Okay, great. So that's our picture. And if our picture is good, it's going to help us check our work, make sure everything makes sense. It's going to help us understand what we're doing mathematically, all the good things. So step one, we can write our givens. This is going to look a little janky, but we're going to do it. We're going to say we first traveled 8 kilometers. This is maybe not the best notation, but it's going to do the job. And my initial time it took to do so is 20 minutes. Again, I'm going to do my unit conversion immediately. Same thing with minutes. That's not the base unit. The base unit for time is seconds. That's the base unit for time. We always got to go to seconds. So I'll give you all a few seconds to see if you can do that. Twenty times 60 equals 1,200 seconds. X2 equals so on and so forth. X3 equals so on and so forth. So I'll leave the rest of those for you to fill out. I don't want to give you all things to do. Step 2, you're solving for displacement. That's delta x, final minus initial. Well, I say final minus initial. Yeah, where I ended up where I started. So try it out, y'all. See if y'all can get this. I'll leave it there. I don't know if that actually ended up being more confusing. I'm just going to put this as delta x equals question mark. I think that's better. Be less confusing. All right. See if y'all can figure out the answer for the displacement. The answers are there. See if you can figure out the average velocity. I haven't talked too much about that, but again, challenge for those that are ready for it. Yes. Good. Good. Yep. I think that helps so. So this takes you like directly. Yeah. No, just straight line. Yeah, this isn't like X versus T. This is more stuff just on moving these and moving this way. That's why they're all straight lines. So at the end of the day, I'm going to challenge to the right. Yep, so you know which route to the right, the left, the right. The question is, I started at 0. How far did I end up? Close enough. 1 to 2%. Good. Yep. As long as you're within 1 to 2%. So I have to check what I did. That was weird. I got these from OpenStax. Sometimes they do some weird rounding. Like we're within 1 to 2%. Don't worry about it. Because it's the final answer. Ironically, I don't really care. I care about the process. If you get within 1 to 2%, your process is solid. Yep. Because time's always. Yeah, you can. Yeah, never. I'll say they go backwards in time.
So our starting point,
0. Just call it 0.
0 and the ending point should be
Wherever you end up. Yep. And the reason we can set the starting point at 0 is because we're finding displacement. So it doesn't matter what your starting point is. You can say your starting point is 4,000 or 5,000 or 6,000. Whatever it would end up being would actually get added to the final and the initial. It's good to, we generally just say we start at 0. Yeah. Yeah, you're good. Nope, that's good. That's the answer. Yeah. Pretend like here. I'm just because I've gotten a question already. I think OpenStax is some weird random stuff. As long as you're within 1 to 2%, you did it correctly, and it's just one of us did some different rounding stuff, and that's good. Yep. 5.1. Yeah. This is not something where I'm like, oh, it has to be exactly this. 1 to 2% means you did the process right. Yes, 100%. All the answers will be back to you. I'm never going to give a question where like 5.1, another 5.11, another answer 5. More than 10. Way more. Generally way more. Generally at least the answer way different. You'll never be able to get the right answer. You'll never get a wrong answer just because of rounding. Yeah. All right, so I think most people have seen this. They've written out their X's, which is great. Negative 3.2 E3 meters. X3 was 16 E3 meters. And I think most people see, you're adding vectors here, y'all. You see in our picture, it's just adding vectors. So delta X is just going to be X1 plus X2 plus X3. And the question, okay, so let me actually maybe write this a little different to maybe make this a bit more clear. Remember, y'all, delta X is X final minus an X initial. What do y'all want X initial to be? Where do y'all want me to start at? Pick a number that's a nice, good number. 0. Let's start at 0, right? Let's make X not 0, because why not? We're allowed. How do we find where we end up? You just add all the numbers. So at the end of the day, you do X1 plus X2 plus X3, subtract 0, and you get how far you travel. That's all you did. If you look at our picture, that's what you did visually. We added vectors visually. Do it mathematically now. X1, X2, X3. All right, so we shove all this up here. And then, yeah, you got your times. I need some space for that. Well, here, we'll worry about that later. So step 4, what is delta X? It's just going to be 83 minus 3.2 E3 plus 16 E3. And you get 20,800. Or if you want 2.08 E4 meters. All right. Now, that's part A. Part A done. Woohoo. Part B is find the average velocity. Part B is actually not too bad, but we got to do a step. And I'm not going to do the step for you, but I am going to finish writing our givens. So our time 2 was 8 minutes. Time 2 was 8 minutes, which equals 8 times 60, 480 seconds. Time 3 was 40 minutes. I'm not doing this one. Well, it wouldn't be terrible. 2,400 seconds. All right, so for part B, we kind of restart the process. Step 2, what are we solving for? Average velocity. Great. And I'm going to leave it there and have you all do step 3 and 4. You've probably already done it. If you have, great, take a breather, do other things. But I'll give you all a few moments if you haven't started this one yet. Yeah, that's good. Yep. Yeah, and that's a better answer than what I have, but I'm purposely this way. I'll fix it. Yeah, I don't exactly. So I got some responsibility facts. They decided to do yours. Like, I don't even know what I do. If you give it them 1 or 2%, it's in the process. And that's it. I don't actually care about the final answer. I care about the process. The final answer is just to show you the process, right? If you give them 1 to 2%, it's kind of like you end up at someone's house, you're like, you follow the right directions. You're basically there. All right, so hopefully you found the equation is that V average equals the change in X over change in time. Oh, look, we found change in X. We already have it. You all just found it. So step 4, all you got to do is plug in the numbers. Well, there's, I guess, one more thing. You got to add up the times. Over all the times added together, what's the change in time? Well, it's 1,200 seconds plus 480 seconds plus 2,400 seconds. And this gives you an average velocity. Which, now, fun fact, when you plug this in, you get something that's like 5.09. You get 5.1 if you round. Now, notice my answer said 5.11. This answer is more accurate. 5.1 is more accurate. And this is a good opportunity because this is always a question I get. Say you get 5.1 and the answer is actually 5. I say actually. As far as I'm concerned, it's the same. In this class, if you're within 1 to 2% of the right answer, you did it correctly and you're good. On a test, I will never give you answers. I will never give you a question on a test where the answer choices are 5.1, 5.2, 5.3. No, they will be significantly different than each other. One answer might be 5.1. Another answer would be like 7.3. Another answer would be like 13.5. They will be significantly different than each other. You can only get close to the right answer within the 1 to 2% or something if you did it correctly. So it's kind of, again, the analogy I give is driving to someone's house. If someone gives you directions and you end up 2 doors down from their house, you're not concerned about that. Like, you're like, okay, I can figure it out from there. As long as you're within 1 to 2%, you did it correct, and that's all I care about. I care about the process. The final answer is whatever. The final answer just helps me confirm that. 1 to 2%, you're good. I get this question all the time. And it's a good question. Last thing I'll mention about this, they don't do this, and I don't know. So this is actually an easy way to catch people that are speeding. It's an interesting one. I don't know why they don't do this. Probably because they don't want to be super mean to people because they'd be really pissed. If you're on the 417, any toll road, they take your toll at each toll. They know what time they take your toll. If they know the distance between 2 tolls and they know the time, they can find the average velocity. If the average velocity is higher than the speed limit, you're speeding. Like, that's something that I don't know, they don't do that. They do that with planes, actually. So, like, you ever hear, like, the people that are, like, they sometimes enforce speed limits with planes. That's one way they do it. They, like, determine when things pass a certain point, and then when they pass a separate point, they know the distance, they know the time, and that's actually how they determine who's speeding. If your average velocity is 80 miles per hour, at some point you were either you've been going 80 miles per hour the whole time, or at some point you were going faster than 80. At some point you would have been going slower, but they don't care about that. They care about that you broke it. So, what's the purpose of average velocity? This is one of them. Another one is this is actually how radar guns work this way. Let me think about this a little bit more. It's a little more complicated. How does a radar gun determine how fast you're going? It knows the speed of light, and then it sends a pulse, and it measures how long it takes for that pulse to return. From that, it can determine the distance that pulse traveled, and from that distance, it then goes backwards and calculates how fast you're going. That's a problem I should probably introduce at some point. At the end of the day, generally, all we can measure is distance and time. Velocity is always calculated. The velocity on your car is actually calculated based on the rotations of your tires. If you know the diameter, I have to double, triple check this. If you know how big your tire is, and you know how many revolutions per minute, you can calculate how far you've traveled based on that. And then you know the time per minute. And that's how your car gets some measure of speedometer on there. I don't know this for sure. One of the things that does raise is, does that mean if you put bigger tires in your car, your speedometer is less accurate? Maybe. I'm not sure. But I think so, given my logic. It's one of the interesting things I have to think about a bit more. All right, great. All right. Last concept I need it so great. We got position. We got velocity. This is the last buzzword I need to cover for you all. And I don't know why I crossed out acceleration. I meant to cross out demo duck. What is the acceleration of Bulbasaur right now? There's Bulbasaur. Haven't taught you what the word acceleration. Take your guess. I'm going to make this one a question because I want to see what you think.
I'm not going to count that. I think we're looking up the story yesterday. Acceleration speed same thing. Oh, no. So what's the difference?
All right, 5 more seconds. 5, 4, 3, 2, 1. Ka-chow. All right. So let's see what these look like. 0, 0. Ooh, people knew the units too. 0, 0, 0. Ooh, I see the -9, the 9.8. That's going to come into play in a bit. Not right now, but future things. All right. So I haven't told you all what the heck acceleration is. But the cool thing is, you have heard this word. If something's accelerating, what's it doing? You've heard this word before. Car is accelerating. What's it doing? Speeding up. If it's decelerating, what's it doing? Slowing down. Now, in our class, we're going to use acceleration for both speeding up and slowing down. You may or may not see the word deceleration every now and then, but generally we'll use acceleration for both. All right, great. What's his velocity right now? 0. What's his velocity right now? 0. Did it change? No. So fun fact, just to give you all, this is going to show up on the next slide. Average velocity is just final velocity minus initial velocity over time. Long story short, it's not changing. There it is in the next slide. It's the next step. So remember you all that, and here I'm going to actually clarify this because this is not quite super accurate.
Yeah, but that's I thought you said the velocity.
Yes, thank you. Yeah, I do that. Do not mix up velocity and acceleration. It will happen to you. A car going 60 miles per hour, a constant 60 miles per hour, its acceleration is 0. Just because you're moving doesn't mean you're getting faster. Just because you're moving doesn't mean you're getting slower. Acceleration is whether or not you're getting faster or slower, whether or not your velocity is changing. It's super, super, super common for people to mix these up. And if you're like, oh, no, I'm not going to mix these up. I'm going to give you all a problem in a bit, not this class, next class, that I expect about probably most people to miss because they'll mix up velocity and acceleration. You'll see. I won't even warn you. And just so you all see the order here, remember you had position. Velocity is your change in position over change in time. Acceleration is your change in velocity over change in time. We just keep dividing by time. That's where the units come from. The units for position is meters. The unit for velocity is meters per second. The unit for acceleration is meters per second divided by second, which is ms squared. That's where the squared comes from. Just keep dividing by seconds. So we'll probably go through this, talk about some graphs, show the kinematics equations, and there's a lot of concepts. Like, my head's starting to feel it. My head's starting to feel it. They're starting to feel it. My brain's starting to feel the we'll call it strain, just from chatting and trying to communicate things. I try not to do too many things in one class. Do enough to get through things, but not so much that people's brains, I'm trying to fill a full cup kind of thing. Boom. All right, here's a question. Car starts at rest and accelerates 12 meters per second in 4 seconds. What is the average acceleration?
Memorize it.
Yeah, so
Yeah.
I need to check
So like, I was like reading all the stuff like how it's different. Yeah.
never take that as like always ask.
So it goes to
Just cringed on it. Threw it all.
All right, 10 more seconds for this. All right, and 5, 4, 3, 2, 1. All right, so we're going to go through all the steps. It maybe sounds overkill, but it's good practice. What's given, y'all? You tell me. It accelerates at 12 meters per second. What is that 12 meters per second going to go with? What variable? Velocity final. That is what I end at. So, if we know what you end at, the natural question is, what do I start at? Initial velocity is 0 because it's at rest. Sometimes in problems we can just look at the numbers, and I will straight up tell you in this problem, you do 12 by 4, yeah, it gives you the right answer. But I'm walking through these skills because there might be a case where that doesn't work out, where if you just divide the numbers, it doesn't work out. So again, it's always the process. All right, one more given. What is it? Change in time. Good. It is how much time has elapsed. Change in time. All right, what are we solving for? Average acceleration. What equation does that? Average acceleration is change in velocity over change in time. Something I'll point out that you all might have noticed I do, it's a tiny little thing. I don't do my V's like this because those sometimes, if you do them really quick, look like a U. So if you notice, I put a little tail on it. That's just a little notation thing. Same thing with T's. Notice I don't make my T's look like this because is it a T or is it a plus sign? Who can say? A nice little notation thing is to put tails on these. These are the little tricks that often don't get mentioned, but as you do enough physics, you start to pick up on them. It's not necessity, but remember, you're gonna make mistakes. The more clear your notation is, the less likely you are to make a mistake. So this is just a little stuff. Same thing, another thing I'll point out is 2s. I do like this. 7s, I put a line through, because if I do a 7 really quick, it looks like a 2. By putting a line through it, now it's a 7. Tiny little things, tiny little notation things that often just get kind of ignored, but almost every person that does physics or math does these little things. 0s, I put a line through, so it doesn't look like an O. If there's ever a letter that looks similar to another one, there's these little notation things you can do to that people often do. So you might notice that as time goes on, I'll try to point them out when I bring them up, when I do them. All right, so yeah, average velocity, average acceleration is going to be V final minus V initial over change in time. You plug in the things. Yes, the math is super, at the end of the day, it's straightforward. Oh, something I want to point out is, again, the units. So if we just look at what we're doing, you do not generally put the units in the math because it just confuses things. But I'm doing this for a purpose to show the units. So it ends up being 12 meters per second over 4 seconds. 3 meters per second divided by second. That's where the units for acceleration come from, y'all. It comes from the math. a lot of our units come from the math. Meters per second divided by seconds, that's meters per second squared. You just chuck an extra s on the bottom, and that turns it into a squared. This can help you kind of check your work in some ways. All right. Next one. An object travels at a constant velocity of 12 meters per second for 4 seconds. What is the average acceleration? 3 meters per second squared, 48 meters per second squared, 12 meters per second squared, or 0 meters per second squared.
It's 12.
Oh. Yeah, there was like one word that changed.
Yeah.
Oh, it's like
But wouldn't that just be 12 minus 2 12 squared divided by 4 is 12?
You're not speeding.
Let me do it. Use my skills. That's true.
That's the. Yeah, it's what it's like. It's classic. Yeah. Alright,
All right, 10 more seconds. All right, in 5, 4, 3, 2, 1. Okay, so this problem, if you notice the one phrasing that differed, that kind of gave us a flag that something's different. So the one phrase that's different is constant velocity. If it's a constant velocity, the definition of acceleration is how much is my velocity change. So the answer is 0. Great. So yeah, that's solid. If you just reckon, and this is one of those, it's a bit more obvious now because we did a problem that looked just like it and some words changed. But this is one of those questions I could ask on a test, and people will don't just take the numbers and divide them. Think through the things. It is one of those, it's so easy to fall into that trap. And if you go through the steps, you can also see this, and this is why I went around and asked people, what's my initial velocity in this problem? 12. It's not 0 because at no point does it say it's at rest. You can't assume it's at rest if it doesn't say so. That's not just something you can assume. If it doesn't tell you the velocity, you cannot assume it's at rest. It's not a solid assumption. Yep, that's totally wrong. Yep, 12. Yep. So we're solving for average acceleration. Same thing. A average equals V. So I'm going through all the steps just because the math always matches that. Long story short, you get 12 minus 12 is 0. You can make this time a million seconds and the problem doesn't change. So. But yeah, and this is it with conceptual questions. If you know what you're doing, they're quick. If you know what they're doing, these conceptual questions are quick. Otherwise, they might take you a little bit more time if you go through the whole process. But both ways get you to the same answer. The math should always back up the concept and vice versa. Okay. Here's a graph. Given the following velocity graph, what is the acceleration at 10 seconds? And I'll even give you all a reminder of the equation. Remember, y'all, acceleration is change in velocity over change in time. Oh yeah, you definitely don't need calculus for this one. And I'm going to zoom in on the graph to make your life a little bit easier.
The velocity over time is the time velocity.
That's totally valid. Looking at this.
So I get to go on my distribution.
So it was like, yeah, so it was a motion where
Right.
like it's not good to know.
What is that all? Visually, what is rise of a run? What does that correspond to? Not the number. What does that correspond to? If you rise or run? So this is rise over run, y'all. Rise over run. That's the buzzword here. What's my rise? How much my velocity changes? What's my run? How much my time changes? What does rise over run correspond to on a graph? All right, give y'all 5 more seconds. In 3, 2, 1. Kaboop. All right, so it's the slope of this line, y'all. That is acceleration. Finding the slope of that line. So what's cool is you could You could do the velocity at 10 seconds minus the velocity at 0 seconds. That's valid. I tended to pick ones that was a bit easier. So to find the slope, I just did these two because the slope at any point on this line is the same. So I did the velocity, the final velocity is 6 minus 0 over what's my change in time. It's 20 seconds. So 6 divided by 20 and you get 0.3 meters per second squared. Oh yeah, be careful, y'all. Let's see how many people didn't notice the bottom. Some people. Okay, that's great. I thought more people would miss that. Always be careful, y'all. There's no rule that says that graphs have to count up by 1. In fact, this would be awful to count up by 1. This graph would be ginormous. Just classic. It's just graph things to keep in mind. All right. Now I'm going to ask you a couple questions about this graph. Then I'll show you all the equations for kinematics. And next class, we'll actually do like a lot of the kinematics math and things like that. But last thing I want to prep you all on is how to actually read graphs. So my question to you all. So I'm just going to use this graph for several questions. I'm going to do 3 different questions. At t equals 10 seconds, is the object speeding up, slowing down? I know it's going to pop over here. Speeding up. All right. At the following times, what is the object doing? I.e., speeding up, slowing down, or constant velocity. So, first one is at 10 seconds. Next one is at 92 seconds. And then the last one is at 98 seconds. All right, and I'll even, just to make this clear, because those last numbers are a little weird, 10 seconds, I'm asking about right here. I don't think this is a super challenging. 92 seconds is that red dot. And then the last one is at the blue dot there. What are they doing at each of the times? So try that out. That one. People are going to put the same answer for B and C.
No, it's a constant summation, but the velocity is because it's something solution. So if the graph is straight like that, we like oh yeah. So what are we measuring?
Well, I was saying it's the same. Yeah. Velocity is constant with the 92.
Which case you go for 0 or is it for the option though? Is it speeding up or slowing down? Break and then accidentally ram stop sign and try to get back.
If you have the same answer for B and C, something is wrong. That's a check for you all. B and C do not have the same answer. And so my hint to you all to help you support you in that, it's all, when it comes to reading velocity graphs, it's all about the zero. Because if your velocity is zero, what are you doing? Not moving. If you're going away from zero, so what does a negative velocity mean? That's the question. So I'll give you all a bit more time to think about B and C. So what does a negative velocity mean? I'm going negative 2 meters per second. What does that mean? I am going back, yeah. I'm going 2 meters per second that way. So yeah, because negative 2 meters per second, negative 4 meters per second. Which one's faster? Negative doesn't put a smaller number here. It just tells you what direction. All right, so we look at this first one, and it's so to figure out whether you're speeding up, slowing down. Just to check, is this a positive acceleration or negative acceleration? It is a positive acceleration. That is true. Now, a positive acceleration does not tell you whether you're speeding up or slowing down. We're going to see that in a second. A positive acceleration does not tell you whether you're speeding up or slowing down. What does tell you is you look at the velocities. As velocity goes, is my velocity going away from zero or towards zero? Away. It's getting a bigger number. So this is speeding up. Which way am I speeding up? To the right. Speeding up to... I ran out of room. Speeding up to right. I didn't ask you to put that, but it's going to help us understand things. All right. Looking at the red dot. Looking at this line. Is this a positive acceleration or negative? It is a negative acceleration, but I told you already the answers are going to be different. At the red dot, am I going towards zero or away from zero? So you are slowing down. But then when you look at the blue dot, are you going away from zero or towards zero? You are going away from zero. This is speeding up. And the reason it's speeding up, just pick a little bit before that. A little bit before that, you're zero velocity. Means you're not moving. After that, it's negative 1 meters per second. What does a negative velocity mean? It's direction. It's not negative velocity. Negative 1 is not a smaller number than 0. It just says I'm going to the left at 1. Negative 2 meters per second means I'm going to the left at 2 meters per second. Negative 3 meters per second. So this is something you got to this is another thing in physics you got to get your mind around. Positive and negative, when it comes to vectors, a negative number is not a smaller number. It's just a number in a different direction. Positive means to the right, negative means to the left. Or positive means up and negative means down. It's one of those mind shifts you got to get around. It's something we do in physics. They don't mean how much. It means when it comes to vectors. All right. Anything to add to that, Peter?
So one thing when I was explaining, speed is the magnitude of velocity. So velocity has magnitude and direction. Speed only cares about the magnitude.
So in the case of the last one, your speed is 1. In the case of part C, your speed is 1. Your velocity is negative 1. It's like you're going in reverse when you have a negative velocity. Concept-wise, great. We got through the things. Again, this is calculus stuff. Don't worry about it. I'm actually going to hide it. Goodbye. Where are you at, Hyde? Okay. So this is what we're going to work on Thursday. And this is the thing that looks intimidating, but all you have to do, so like the example I gave here, if I gave you x initial, x final, a, and t, and I want to find final velocity, I just find all the equations with final velocity. And then I find the equations with the things that I have, which are all these things. So x initial, x final. And you just go through this, and we're going to practice this next class. I missed the initial here. So we're going to practice this next class. This is going to look intimidating, but all I need you to know is if you can write down your givens and your missings, just find the equation that has them all, and that's all we're going to have to do. That's the skill to solve these problems. It's very straightforward, way easier than it looks.
Also, you may have seen this on web courses, but I'm offering.
Yeah.
I have a microphone. Okay. You may have seen this on web courses. I sent out an announcement. I am also doing office hours. My office hours are Fridays at, did I say 2:30? I think I said 2:30. Whatever I said in the announcement, I think it was 2:30. Also in Physical Sciences building, it's room 355. So you go up to the third floor. There's the two hallways that cut across the building, and you take the left one that goes to the back, and it's most of the way along that center.
4 different places y'all can go to outside of any friends that you all know. So many resources.
Have a good day.
Have a good one.
I have a question. The quiz that's on Friday, is that on just the